So everything we see in the universe, the stars, the planets, the galaxies, the plants, the rocks, the clouds, us, everything you say, it's, to me, at the front of this book, is what you call the product of a remarkable asymmetry of matter over antimatter. What did you mean by that?
So profound asymmetry. So you just went right into the stuff there.
Yeah, well.
Okay. Just a quick note.
Yeah.
That this title, Astrophysics for People in a Hurry, I've had people joke with me about it, say, oh, was Astrophysics for Dummies already taken, you know? And I just wanted to make it clear that first, yes, it was taken, but that's, but there's nothing, I don't think there's anything, quote, dumbed down about the astrophysics in this book. It's all sort of curated, legitimate, full-up astrophysics in an attempt to sort of grant the reader a degree of fluency in modern astrophysics, so like the next morning at the water cooler, you could just be talking about.
Yeah, and like there are things in here that I had never heard of.
Really? And you and you get around.
I get around.
Yeah, you get around.
So I'm going to be checking. But
so in the early universe, the temperature was very hot, and above certain thresholds of temperature, what happens is matter no longer stays as matter. It can freely move back and forth between itself and energy. And we have the recipe for this. It comes from E equals mc squared. We all know that equation. It's the formal conversion recipe for matter and energy. And the c squared is the speed of light squared. It's a huge number. A little bit of mass times that huge number gives you a lot of energy. We don't experience in our lives E equals mc squared because the energy in which we're immersed is not high enough to enable matter to go back and forth between energy and itself. That's why it took so long to discover E equals mc squared and to come to terms and to come to understand it. But it is a profound equation that manifests from the beginning of time all the way to the future of the universe, but not in our life experience. All right, so, and also let me preface it by saying, in one of the opening pages of the book, it's, what do you call it?
yes, the universe is under no obligation to make sense to you.
Yeah, that's it.
Signed by you.
That's what I wanted to make that clear. So the universe is under no obligation to make sense to any of us. So I'll be saying things and you'll say, that doesn't make sense. Just remember what I just said, okay? Okay. What we've learned is that the universe is what we measure it to be, not what we want it to be, not what feels good, not what only has to make sense to our five senses. Our five biological senses forged in the plains of Africa, you know, 1 million years ago, 500,000 years, whatever, what's the latest the biologists tell us, is those senses, to prevent us from getting eaten by a lion, are very different from what you need to grasp the universe. And so this is why mathematics is so potent, because it takes us out of our senses and enables us to still probe the reality of what the universe is. So here's what goes on. If matter and energy can go back and forth, this is how that works. I have a blob of energy and it decides that it wants to become matter, and it does. So all this energy becomes matter.
What do you mean it decides?
It happens spontaneously, and it depends on what the temperature is.
Okay. Cool.
What's that?
It's hot and then it gets cold.
Yeah, so if the temperature drops too low,
yeah,
then it's not going to happen. The energy will stay energy, and whatever matter was around at that time will stay matter. So watch what happens. We now have high enough energy that if you converted this pocket of energy into mass, E equals mc squared, you get enough mass to create particles out of. Okay? Mm-hmm. So get a very low, take an electron, for example. That's very low mass among subatomic particles. So you can ask, how much energy does it take to make an electron? Write that number down. If you don't have that much energy around you, your energy will never become a particle. Ever. Okay? So in the early universe, there was so much energy, every particle could be made. So watch what happens. You have a pocket of energy, it becomes mass. And the only way we know that can happen is if it becomes a particle and an antiparticle pair. Matter and antimatter.
Antimatter is the opposite of the first thing?
Yes.
Oh.
In every measurable way.
Huh.
Okay, so the opposite of an electron is a positron. It looks just like an electron, but among other things, it has the opposite charge of an electron, positron. Okay? Every particle has an antiparticle.
Does a neutron have an anti-neutron?
Yes.
Does a proton have an anti-proton?
Yes. And so you might say, well, what's the opposite charge of a neutron? Because the neutron has no charge.
Yeah, I know.
But you look at what the neutron is made of. It's made of quarks that have fractional charges that cancel each other to get zero net charge on the neutron. So an anti-neutron has all those same quarks, but the antimatter version of those quarks on the inside.
What will happen if these two kiss?
If you take matter and antimatter and put them together, they annihilate and become pure energy, and the matter disappears entirely.
What do you mean disappear? Does it leave something over?
No, no.
What, not even like a little boing? Not a light, a photon, something?
Yes, yes. So you take the particles, matter, antimatter, identical particles, except that they're matter, antimatter, bring them together, they disappear. And that matter becomes energy, and all that's left is energy. Right in that pocket, right there. That happens all the time in the center of the sun. It happened everywhere in the early universe. Now here's the rub. You have all these photons of light. Oh, by the way, I have a photon joke. Can I tell it?
Tell the photon.
Okay. A photon checks into a hotel.
Not a bar. A hotel.
Not a bar. No,
Okay.
this has to be a
It
hotel.
can't be racy because this is a family.
I got this.
Okay.
I got this. Photon checks into a hotel. The bellhop comes up and says, do you have any luggage? And the photon says, no, I'm traveling light. So when I say pocket of energy, let's just simply refer to photons because they carry energy. All right, so a photon turns into matter. It's a matter-antimatter pair. Matter-antimatter come together. They make a photon. It's symmetric. Okay?
Okay.
So,
Wait a second. Does that mean that if every matter part met every antimatter part, they all would go and you'd be left with just light?
yes, there would be no matter in the universe, only light. So you have all this energy in the form of photons becoming matter and back and forth, and there it goes. As the temperature of the universe dropped, you reach a point where you can no longer make particles with the energy you have. But you have all these matter and antimatter particle pairs that eventually find one another and annihilate and make a photon. But we're still cooling the universe. So, according to our known laws of physics, in the cooling universe, every matter and antimatter particle pair would have annihilated, made a photon. The photon would have cooled, and no more matter would have been made, and we would have had an entire universe of just light. But that is not the universe we occupy. So, mysteriously, we call it symmetry breaking, just because that's what happened. We're just describing what happened, not that we fully understand why it happened. One out of basically 1 million of these reactions, 1 out of 1 million, the photon did not make a matter-antimatter pair. It just made a matter particle.
It was very...
You're trying to find out why.
Yeah.
And I'm just saying, it is that. Okay? So, 1 out of about 1 million makes a matter particle without the antimatter counterpart. So now the dance card, the dance hall, has 999,000 partners that can pair up.
999, 9,000, yes. Well,
1,999,
Yeah.
and there's one left over. So everybody else becomes light, and that one has no antimatter particle to mate with. And it is frozen out of the universe and has become all the matter that we know and see today.
So everything that we are...
It is a profound asymmetry
Wow.
in the early universe.
We're the stuff that didn't get a date.
Correct.
Doesn't that strike you as an extremely fragile interpretation of all that there is? I mean, it's like being around by the skinny skin of your chinny, whatever that thing is.
Except in the concept of multiverse, where you'd have many, many universes, all the laws of physics don't have to be the same in each universe. So there could be plenty of universes where the dance card was full and they just have light in them, and you are not in that universe saying that it was just a chance occurrence.
Oh, well.
You are in the universe
I
where
don't care
it
about
happened.
the other ones. I'm just interested that our universe, the one that we know and live in, is such a fragile arrangement
No,
originally.
it's not. Well, it doesn't have to be. It may be, but it doesn't have to be,
Yeah.
and it is unlikely to be. And can I give an obscure example that will settle this?
Yeah.
Okay. Line up 1,000 people and give them a coin, and everybody's have. Have them flip. Half get heads, 250 of you sit down. Now we're left with 250. Do it again. Go from 250 to 125 to 60 to 30 to 15 to 8 to 4 to 2 to 1. Okay? In this experiment. It's not an unthinkable experiment.
Mm-hmm.
This person who survived this exercise flipped heads 10 consecutive times. Now, here's what journalists do. They go up to that person and they say, "How do you feel?" "Well, I knew I had felt that head's energy halfway through, and I was feeling it, and did they ask anyone else if they felt that head's energy?" No, they only interviewed that guy. Okay?
You come
Wait,
on to...
I'm not done.
All right.
Wait, so that person says, "Boy, I was lucky to flip heads 10 consecutive times." Well, essentially every time you do this experiment, somebody's going to flip heads 10 consecutive times. So you want to say, "Oh, this is a special universe in which that happened." No, because of the nature of the fact that you have 1,000 experiments happening all the time, there's going to be one where somebody flips heads 10 consecutive times. Every time you do this experiment. That does not make it special. Just because somebody flips heads 10 consecutive times every time you do the experiment. So, you're in a universe where this weird thing happens at the beginning, and you want to feel all heads energy about it. And I'm saying, in a multiverse, there could be 999 universes where that did not happen. And you're in the one that did, and you want special credit for it. I'm not giving it to you.
All right. Let me move on to another thought. In the second sort of section of this book, this is something that hasn't really occurred to me. I mean, once upon
Wait, the book doesn't have sections.
I know it doesn't. I just meant the next thing I noticed.
Okay.
Speaking of universes, there was a time when people believed that the heavens up there were the province of God, and whatever was going on in there was unknowable, and it would be basically sinful to find out. You point out that with gravity, well, why don't you just briefly, Newton comes along and then everything changes.
Yeah. So you look up and the planets are going forward against the background stars and then backwards, and we call that, there's a word for that, retrograde, and they do the loop-de-loop, and nobody understands it. And the fact that no one understands it is presented as evidence in some bits of scholarship, as evidence for the divinity of the heavens, because that is the handiwork of God, and we are mortal, and God is immortal and omniscient, and so we can't possibly know the mind of God. So you're just content just in your ignorance watching planets. There was some attempts at this with the geocentric epicycles and all of this, but it was well accepted that you'll never understand. Newton comes along, writes down equations of motion, equations of gravity, and kind of on a dare, he invents integral and differential calculus. Then he turned 26. This is why Isaac Newton is my man, okay? Just to make that clear.
Okay.
Among many reasons. But so he writes down these equations, and he can now demonstrate full knowledge of how, why, and where, and what the planets are doing. And so potent was his new theory of gravity that it worked for moons of Jupiter orbiting Jupiter, not just planets orbiting the sun. And this was the first indication, maybe this is not just a local truth, that maybe it applies across the universe. And this was a little bit of heresy, thought by some. That, in fact, Newton was accused by some say, Isaac, you've left nothing for God to do. And that's simultaneously a dig at him, but also quite a compliment, that he can actually understand the mind of God.
Well, this is where it got interesting. Then you went off. I mean, everybody knows that gravity is apparently ubiquitous and universal. But then you went and asked about chemistry and physics, constants, and I hadn't really thought about that before. Is the chemistry of the sun and the chemistry of the earth and the chemistry of the furthest thing you can think of, are the laws about bonds and pairings and so, are they the same everywhere without exception?
It was not obvious. There's no tablet in the sky that required that the laws of physics we discover on Earth's surface would apply elsewhere. If they were different on Earth than on the moon and on the sun, I suppose we could deal with that. But what a remarkable fact that it is the same.
Well, wait a second. Like, you've seen that thing on Jupiter, that storm that never quits? The big red thing, the big...
Yeah, we call it, the red spot on Jupiter, we call it Jupiter's red spot.
Okay.
Because that's how we roll.
That thing is...
Spots on the sun, sunspots. See? See how... Any geologists or chemists in the audience? Biologists?
But
you should be jealous of this fact. Because you guys name stuff that nobody knows what the hell you're talking about. Okay, and you know what I'm talking about.
Isn't it suspicious to you that a storm there could go on for 350 years without a break, and we never have storms that go on for 350 years without a break? We don't even have storms that go on for like 6 weeks without a break.
So, first of all, these storms are, when we have storms, it's in our atmosphere, so that's gas.
Yeah.
We rotate once a day, and so that rotation creates what we call a Coriolis force, which moving air that moves from one latitude to another, actually has its direction deflected because of this Coriolis force, and this is why storms rotate in one direction, counterclockwise in the northern hemisphere, and clockwise in the southern hemisphere. Just a quick aside, I was channel surfing one day, waiting for a movie to come on at the top of the hour, had 15 minutes, I hit a football game, and they just ended the game at a tie, and they just started overtime. I said, that's about right. Let me just watch this. How bad could it be? After the necessary exchange of possession, it became sudden death overtime. And then one of the teams, Cincinnati Bengals, got within 50 yards, and they kicked a field goal. And the ball rotated up. It hit the left upright of the goalpost and went in. And I said, ooh, wait a minute. And I said, which stadium is this? What's the latitude? And I looked at the orientation of the stadium, I did a calculation, and then I tweeted. And I said, the overtime winning field goal by the Cincinnati Bengals was likely aided by a 1/3 of an inch deflection to the right imparted by Earth's rotation.
Which
People lost their minds. People Oh, the local sports channels. And so the point is, if you are going north-south at all in the northern hemisphere, you will deflect to the right, no matter what you're doing, okay? That's why you have a low-pressure system, and I'm a ball of gas below it. If it's low pressure there, and I'm air, I'm gonna head for the low pressure. That's how this works. It's low pressure. That means there's higher pressure out here, so all the pressure is gonna send me in that direction. But I'm crossing lines of latitude. And so Earth's rotation will deflect me to the right. How about what? How about air that's above it? It says, I see a low pressure system. Let me go to it. So it goes to it and it deflects to the right. So all this air deflects to the right, but it's still trying to get to the center of the low pressure system, but it can't because it keeps getting deflected. And all this deflection becomes this cyclonic energy that turns into a storm. And that is how you get hurricanes, tornadoes, what do you call it? Cyclones.
Cyclone.
Okay? Okay.
So we're back at Jupiter finally.
Yes, we are.
Yes.
So now watch.
Oh, good.
So this happens in the gas.
Yeah.
All right. The Coriolis force is heightened if you spin faster. Okay? And so what is Jupiter? It's 100 times bigger than Earth. More than that, 10, 1,000 times bigger than Earth. It's like, it's 10 times across, cubed. So it's 1,000 times bigger than Earth. It's mostly gas. And it rotates once in about 10 hours. You want to talk about ferocious Coriolis forces? We have storms that last weeks here. Hurricanes that pick up and they go weeks on this little speck we call Earth that has this much atmosphere on it. Go to a planet that rotates twice as fast, is 10 times as wide, 1,000 times the volume, and is mostly gas, and you're complaining that it lasted 300 years?
You are really good. All right,
No.
Can you spontaneously levitate and hover above the ground in a lotus position like Michael Keaton in Birdman? In the the beginning of Birdman when he's with his underpants. Forget the underpants, just the levitation. This for some
Is that your first thought when you think of someone in a lotus position? Is Michael Keaton in that movie?
Yes.
Okay.
Yeah.
Yeah. It's just there's certain things you just can't do because they're prevented by all known laws of physics. You cannot spontaneously set yourself into motion unless you push off of something else or you lose some kind of mass that was within you. So rockets, when they take off, they're ejecting mass out the other side, okay?
Wow. So do you saw Birdman? Did you just leap up from your seat and say, can't do that, can't do that?
No, there are movies where I'm prepared to suspend my disbelief, yes. Like, just as an example, I was asked about the movie Guardians of the Galaxy. And they asked me, well, the ships that are going through space, they make noise, and clearly, does that upset you? Because in space, where there is no air, no one can hear you scream. But no one can hear you explode either, nor will you hear engines or anything. And so they said, does that upset you? And I said, I bought into the idea that this movie has a talking raccoon that shoots artillery from heavy weaponry off its shoulder. If I can accept that, I'm good with whatever else they deliver in the film. So I have the capacity to accept movie magic. Yes.
What would happen if someone served you a hot cocoa with whipped cream and you see no whipped cream in evidence?
Oh, don't get me started.
Okay.
Oh, wait. Let me finish about levitating.
Please.
Right. So all the people that are levitating, it's some kind of an illusion that they're not telling you about. Okay. Period. Okay. Now, but if you really want to levitate, if this is really important to you, I tried to calculate how many cans of beans this would require. Then you got to kind of hold it in.
Yeah. Right.
Then let loose.
Suddenly.
Suddenly.
Yes.
And in principle, for the duration of the thrust, you can levitate briefly.
But this would argue against the lotus position, because there would be an opening so suddenly that there'd be too much, too soon, too fast, and therefore no rise.
Oh yeah, you wouldn't, well, you could stay there if it just kept coming in, right. So it's not impossible to hold a lotus position. It's just unlikely you're doing it for these other ways that are described.
I see.
Yes.
The cocoa?
Cocoa. Oh yeah, so there was an incident in Pasadena, California. I was there. I don't drink much coffee. I don't have a relationship with caffeine, but every now and then I'll be delighted to have a nice cup of hot cocoa. And I went to one of these coffee houses, with the chalkboard out front. And so I had, the kind I'm talking about. They're all over Brooklyn. You trip on the chalkboards in Brooklyn. So I'm in there, I order hot chocolate. And I ordered it with whipped cream, of course, right? And it comes to the table, and there's no whipped cream. And I said, I ordered this with whipped cream. And they said, oh, we put it on. And I said, well, where is it? Oh, he said, it's sunk to the bottom. I then said, either the laws of physics that apply everywhere in the universe are suspended in your coffee shop, or you didn't put whipped cream on my hot cocoa. And he looked indignant.
Really?
Now, to his credit, rather than continue to argue with me, he intended to prove me wrong.
Whoa.
So he went into the kitchen, brought out the whipped cream, scooped it up, popped it in my hot cocoa, and it bobbed once and floated atop. And there it was.
Did you invite him?
Of course, whipped cream has to float. Because, first of all, before it was whipped cream, it was cream, okay? And old-timers remember, what does cream do in unhomogenized milk? It floats to the top, and you skim off the cream, leaving behind skim milk, okay? This is how that works. Now, you take the heavy cream and then whip it, putting air into it. It is not gonna sink on any known liquid devised by man, okay? So,
all right.
So here's my point. The lesson there is,
Yes.
I'm a fan of the edict, if an argument lasts more than 5 minutes, then both sides are wrong. I think that applies maybe 85% of the time, but it's a good rule, it's a good tenet to carry with you. Now watch. This is how science works. One researcher comes up with a result, and that is not the truth. No. A scientific emergent truth is not the result of any one experiment. What has to happen is somebody else has to verify it, preferably a competitor, preferably someone who doesn't want you to be correct, such as my waiter. He went out to prove me wrong and got the same result that I had declared. We can call that the beginnings of an emergent truth about whipped cream. Now we need someone to do it in Asia and in Europe, and then you get a trend, and you can then declare that a consensus of observation and experiments has emerged in the scientific community. Whipped cream floats on hot chocolate.
And that waiter today is getting a PhD in buoyancy. Let me go on to a question that came up later in the book. Just how voidy is the void of space? Like, so it looks pretty empty out there between galaxies, just a lot of black, it seems anyway. If you stepped into intergalactic space, by the way, what might happen to you?
You die.
Yeah. Yep. But you might see stuff, and this is the list. Well, I had never heard of any of these things. Dwarf galaxies, runaway stars, faint blue galaxies, hot clouds that emit X-rays. Let me just ask you about some of them. What is a dwarf galaxy?
It's a little galaxy.
Well, that I figured.
Didn't we go through this already? Our words mean what they say?
But
we're past that already.
There are galaxies that you see, the ones the Magellan saw, smudges in the sky. Those are huge things.
No, well, they're dwarf galaxies.
Those are dwarf galaxies?
Oh, yeah.
Oh.
Oh, yeah, they're like 100th the size of our galaxy.
So how many dwarf...
They far outnumber big galaxies.
They do.
Yeah, so maybe we shouldn't be calling them dwarfs, because they're the common size galaxy. We should just be called giants, perhaps.
Giants galaxy.
And they call them regular.
Right?
That's how that works, right?
What is the difference?
Right?
How many stars are in a galaxy?
Our galaxy has several 100 billion stars.
And in a dwarf galaxy?
At most, 1 billion, but more typically hundreds of millions. These are small numbers compared to full-up red-blooded galaxies. So tiny are dwarf galaxies, and we tend to find them in the vicinity of big galaxies, but you know what happens? They orbit the big galaxy, but their orbits are not stable, and they do a death spiral in, and they get eaten by the larger galaxy. And we have a term for that. It's called galactic cannibalism. In fact, there are streams of stars that we see in our own galaxy that have the same trajectory as one another through the stellar system that is the Milky Way. So and you follow it, and it comes back out and back in again. And so this is evidence that this was once a fleshy but dwarfy galaxy that we ate, ripped apart. And now the stars are just trying to have the last bastions of a memory of what they once were, because they're getting stretched apart by what we call the tidal forces of our galaxy.
Does the Milky Way have dwarfs?
Yeah, it has the first science essay I ever wrote was called "The Galaxy and the Seven Dwarfs," because at the time the Milky Way had 7 dwarf galaxies in orbit around it, and then but dwarf galaxies are very small; they're hard to detect. And since then, we've discovered, a couple dozen more. So we might be up above 2 dozen dwarf galaxies in our vicinity, basically nearby. So the point, getting back to the void, is you look out in the void, you say there's nothing there. Well, what are you invoking to declare that it's a void? Is it your eyes? Well, let's bring in a telescope. Are you using visible light? Is that a visible light telescope? Bring in an X-ray telescope, an infrared telescope. Bring in the spate of senses that science has developed that transcend the 5 native senses we have through our human physiology. And that power enables us to decode the universe not as our senses receive them, but as our detectors.
There is an amazing chapter, or coda, somewhere in the back, where you find out how human beings finally sensed what they couldn't see. That there is a rainbow of color that we all can see, which are waves of different lengths. They take you from whatever it's, Git B, Vidbo, Roy B, Viv. So, Roy B, Viv.
Roy.
Red to...
Repeat after me, Roy.
Red,
Roy,
orange.
G, Biv.
Red, orange, yellow, green, Biv. Blue, indigo, violet.
Violet. You got it.
But it's weird.
Just a quick thing. Roses are red, violets are violet. Right? Who came up with violets are blue? What is that? We have a name for that color.
That was a desperate poet looking for a rhyme, I think.
Don't be violating laws of physics just to make the rhyme, okay?
I was going to say...
Do you know Mark Twain's edict that I love?
What is it?
First, get your facts straight, then distort them at your leisure.
Well, let me just finish this thought, and then I've been commanded to ask questions.
I'm sorry.
At the end, there's this moment where somebody has to figure out that there might be something redder than red, or somehow more than violet. Now, we only have eyes, but this particular person used a thermometer.
It was brilliant.
It was brilliant.
Brilliant.
Yeah.
Okay, so Isaac Newton is the first to understand that white light is composed of colors. So he takes white light, puts it through a prism, and he gets Roy G. Biv. Actually, the indigo, he had a mystical fascination with the number 7, so he wanted to lay down 7 colors.
Oh.
But indigo is just really blue-violet, all right?
Okay.
But anyhow, we'll give him his indigo because he did all that stuff before he turned 26. So if you invent calculus just on a dare, we'll give it to you, all right? We'll give you indigo if you need to have indigo. So he's got the colors, and then he took those colors, merged them back together, and he got white light out the other side. That's some freaky stuff. That's just freaky.
Yeah.
That red, orange, yellow, green, blue, violet equals white. Okay. So we're good there. William Herschel comes around later and says, I wonder, just to even ask this question, I wonder if the different colors of light have different temperatures. So he laid down the spectrum with sunlight prism, and he put a thermometer in each color. And then he had an 8th thermometer. I don't know if he used one and did the experiment 7 times, but he had another thermometer that he used as the control thermometer. You put that over to the side where there are no colors. And that would presumably just measure the room temperature. So he knows enough to even think that this is an interesting exercise, and he's got a control thermometer. And he just puts it over to the side of the red, out of sight. And then he watches the thermometers. And the control thermometer goes through the roof.
Yes, it does.
And he's looking at it, and he says, something must be coming through the prism that I cannot see. And he describes this as light unfit for vision.
Yeah. Yes, he does.
He discovers infrared light with that experiment.
And then another guy
Which the human eye cannot see.
It's
and if you go to the hardware store and get an infrared bulb, and you turn it on and it looks red, you're seeing the red light that is also emitted from this infrared bulb, and the heat that you feel, your eye cannot see, that's all the infrared that you're buying when you pay money for that bulb. Yeah.
And then some other guy put a piece of paper on the other side of violet, and it turned dark, and he pretty much
photographic paper.
Photographic paper.
And he found that it responded in the way you would normally respond by putting photographic paper in front of visible light. So he concludes, that was somebody else later.
Somebody else, yeah.
Right, and says, there's something beyond the light. There's something less than the red, infrared, something beyond the violet. And thus was discovered ultraviolet light. And so to pose the question in the first place was a stroke of brilliance. To then trust your measurements on a level where you then declare you have made that discovery is a whole other thing.
Yeah. Here's the thing about this book.
Well, that story is told in the book, just so people get a sense of the history of the history of puzzlement and the history of discovery rolled up into one.
I'm not going to ask you about anything else because it's time for questions and answers.